Where is everybody? That 27-inch question, short, plain, and oddly poetic, was posed over a casual lunch in 1950 by Enrico Fermi. It was a spark, a tiny exhalation of curiosity that would ignite decades of debate, science, and imagination. Today, that question has a name, the Fermi Paradox. It is the elegant mismatch between a simple calculation and a stubborn silence. The universe is colossal and ancient. Our galaxy alone holds hundreds of billions of stars, most with planets of their own. So why, despite the cosmic abundance, do the skies seem so empty of intelligent neighbors? Imagine, for a moment, standing on a quiet beach at dawn. The ocean stretches forever, and you know there are countless other shores. Yet no footprints disturb your sand. That image captures the emotional thrum of the paradox, curiosity mixed with unease. In the next several minutes, I'm going to guide you across a landscape of ideas, historical roots, probabilistic thinking, scientific searches, and bold hypotheses. We'll move from the lunch room where Fermi asked his pointed question through equations and telescopes, and into thought experiments that touch on ethics, risk, and our cosmic responsibilities. The journey is meant for anyone who wonders not only whether we are alone, but what that might mean for our future. First, let's trace the story back to its origins. Fermi's question wasn't the flourish of a mystic. It was the product of practical reasoning. If even a modest fraction of stars hosted life that developed technology and the ability to travel at a fraction of light speed, then colonizing the galaxy could, in principle, take only millions of years, an instant compared to the galaxy's age. Michael Hart later sharpened the argument in 1975, arguing that if interstellar travel is possible, extraterrestrials should have been here by now. Frank Tipler then added a mechanical twist, self-replicating probes. In his view, a civilization could launch machines that build copies of themselves, sending exploration sprigs outward that multiply exponentially, sweeping the galaxy long before humans appeared. The absence of such probes, Tipler said, suggests a stark conclusion. But science is rarely so cleanly decisive. Over time, critics pointed out that motives, costs, and cultural factors complicate the idea of inevitable expansion. That disagreement opened the door to a rich, sprawling set of possible answers. To bring some order to that chaos, astronomers often point to a useful tool, the Drake equation. It was created not as a final answer, but as a way to organize our thinking. The equation multiplies a chain of factors: how many stars form each year, how many host planets, how many of those planets can support life, how often life actually starts, how often intelligence evolves, how many civilizations develop detectable technology, and how long those civilizations release signals we could notice. Some of those factors are now clearer than they were in 1961. We know planets are common, thanks to Kepler and other missions, and Earth-sized worlds in habitable zones are not rare. But the tough terms remain stubbornly uncertain. How often does life begin? How often does intelligence arise? How long does a technological civilization last? Those last unknowns turn the equation into a canvas of possibility, producing estimates that can stretch from "we are alone" to "the galaxy thrums with civilizations." That uncertainty invites different styles of answers. One family of solutions says life is rare. Maybe the Earth is a freak of fortune. This is the essence of the rare Earth hypothesis. Certain combinations, like a large stabilizing moon, plate tectonics, a protective giant neighbor like Jupiter, and a place in a calm galactic neighborhood, might be uncommon. If so, complex life could be an extraordinary fluke. Another possibility in the same vein is that we are simply early. The universe has matured over cosmic time. Heavy elements needed for life were forged in earlier generations of stars. Perhaps Earth arrived relatively soon, and the galaxy has yet to produce many technological civilizations. Those rarity explanations are comforting in one way. They suggest that humanity may not face some universal doom. Rather, life is precious and possibly unique. Contrast that with another family of answers that are darker, the Great Filter hypotheses. Coined by Robin Hanson, the Great Filter imagines a narrow doorway in the timeline from raw matter to spacefaring civilization that almost every trajectory fails to pass through. If that filter lies behind us, say the origin of life or the rise of complex multicellular organisms, then we are among the lucky few who beat the odds. If the filter lies ahead, nuclear war, runaway climate collapse, unaligned artificial intelligence, or some technological catastrophe, then our silence in the sky is an ominous sign. It means other civilizations, likely self, destruct before they can broadcast themselves across light years. The Great Filter flips the question from where are they to what must we avoid. It becomes less an astronomical riddle and more a moral and practical warning about stewardship of our technological future. Between rarity and doom, there's a middle ground. They might exist, but we simply don't see them. Observational limits are real. Our telescopes and radio dishes have searched only a sliver of the sky and a sliver of the electromagnetic spectrum. The search for extraterrestrial intelligence, SETI, has matured from amateur radio projects to professional programs like Breakthrough Listen, scanning millions of stars across many frequencies. Yet the galaxy is vast, and signals may be rare, intermittent, and short-lived. Civilizations might use communication channels we barely monitor, neutrinos, laser pulses, or ways we haven't even imagined. Advanced civilizations might also evolve toward efficiency and low waste, emitting so little leakage that our instruments cannot pick up their presence. Think of a city that switches off its lights and goes underground. It doesn't show up on a distant observation of emitted photons. Then there are strategic or sociological answers. Perhaps advanced civilizations deliberately avoid contact. The zoo hypothesis suggests Earth is being observed but deliberately left alone, like a wildlife preserve. A broader prime directive idea imagines a galactic ethic, non-interference, so that young civilizations can evolve without outside influence. Another poignant variation is the dark forest notion, popularized in fiction and supported by game theoretic thinking. The universe is dangerous, and silence is survival. Revealing one's position could be reckless, so every intelligent polity keeps quiet to avoid attracting predators. In such a cosmos, quiet is rational caution, not evidence of absence. There's also the provocative simulation hypothesis. If our reality is a constructed simulation, then the parameters of our digital cosmos could be set to focus only on human development and not render alien civilizations in detail. The simulation designers might have reasons to create apparent isolation, computational efficiency, experimental control, or narrative economy. While unfalsifiable, the simulation idea reframes the paradox as a design choice rather than a natural fact. As we sift through these options, fresh data keeps reshaping the debate. The exoplanet revolution changed everything. Kepler revealed that planets are common, and systems like TRAPPIST demonstrate compact systems with several Earth-sized worlds. Astrobiology broadened the palette of possible habitats. Extremophiles on Earth thrive in boiling vents, acidic pools, and subsurface ice. That resilience suggests life might pop up in places once considered uninhabitable. We've learned to look beneath planetary surfaces, to moons like Europa and Enceladus, where oceans hide beneath ice, heated by tidal forces. But abundance of life, bearing worlds, doesn't automatically imply abundance of detectable civilizations. Many worlds may host microbial or subsurface ecosystems unsuited to developing radio telescopes and starships. Modern SETI has likewise evolved. It no longer looks only for distant, hello radio beacons. It searches for technosignatures, laser flashes, atmospheric pollutants, megastructures that dim a star's light in tailways. Projects like Breakthrough Listen apply sophisticated algorithms to hunt for unusual patterns in enormous datasets. Citizen science projects have engaged the public, and machine learning helps flag anomalies. Yet even with these tools, detection depends on timing, method, and patience. A civilization that transmitted brightly for a century a million years ago might be long gone, leaving only an echo we might never know to look for. Philosophy and risk analysis braid through the paradox too. If silence is a sign that technological civilizations tend to erase themselves, that has a sobering lesson. The same advances that promise abundance, nuclear energy, synthetic biology, powerful AI may also be doors to extinction. Recognizing that possibility focuses attention on existential risk mitigation, building resilient institutions, tempering risky technologies, and cultivating global cooperation. Alternatively, if silence arises from intentional restraint, universes full of civilizations that quietly cultivate sustainability and non-expansion, then their example may suggest a different future for us, one that values longevity over growth. In both cases, the Fermi Paradox becomes less an abstract puzzle and more a mirror held up to humanity's choices. Another intriguing branch of thought imagines civilization trajectories beyond our anthropocentric expectations. Some thinkers propose that advanced minds may shift to digital substrates, biological entities that compute in dense, efficient environments and minimize their physical footprints. Others hypothesize a transcension. Civilizations compress their activities into tiny, information-dense regions, perhaps near black holes, effectively disappearing from our ability to observe. If intelligence tends inward rather than outward, it would leave the galaxy strangely quiet even if minds are abundant. We must also reckon with biases. Our assumptions about communication, expansion, and technological aims are derived from human history. We expect radio beacons because we built radios. We expect starships because we imagine exploration. But alien intelligence might have entirely different motivations or constraints. Temporal myopia also matters. Civilizations might arise in different epochs, separated by millions of years, an astronomical blink. Our brief existence so far gives us an inadequate sample to judge frequency and timing. The universe could host civilizations that bloom and fade long before or after our era. So what can we do with all these possibilities? Practically, we keep searching, but more wisely. Improved telescopes will characterize exoplanet atmospheres for biosignatures, oxygen, methane, and other chemical hints that life may be reshaping a world. Continued investment in technosignature hunts broadens the net. Lasers, narrowband radio, waste heat from advanced engineering. Simultaneously, the paradox nudges us toward taking our own future seriously. Whether the great filter is ahead or behind, the stakes could not be higher. Policies that reduce existential risk, promote global cooperation, and guide safe development of transformative technologies are pragmatic responses to an uncertain cosmic context. There is also a poetic and ethical dimension. If we discover that life is common but intelligent life rare, we inherit a profound stewardship role. If life is rare in the galaxy, then the value we assign to Earth's biosphere grows immeasurably. Conversely, if we discover abundant life everywhere, microbial oceans on icy moons, primitive ecosystems on exoplanets, that would redefine what it means to be special. The emotional reaction, either way, is worth considering. Awe at company in the cosmos, or solemn responsibility when solitude is confirmed. Finally, some speculative but constructive ideas have emerged. Directed panspermia suggests intentional seeding of life across worlds. While morally fraught, it offers a model for how life could spread without physical travel of organisms. Meticulously designed messages, should we ever send them, must consider who speaks for humanity and the long time lags of interstellar communication. Debates about active messaging meti weigh the scientific curiosity against potential risk. Broadcasting our existence might be an invitation or an act of vulnerability. In closing, the Fermi Paradox persists because it sits where many big unknowns converge: astrophysics, biology, technology, and ethics. It resists tidy solutions because the universe is generous with scale and stingy with samples, but that very resistance is fertile. The paradox pushes us to refine our search strategies, to cultivate humility about our assumptions, and to take seriously the long-term survival of our species. Whether the answer is comforting or cautionary, the search itself is a noble human endeavor, an expression of curiosity and courage. So as you look up tonight and watch a point of light travel across the sky, remember the layers of possibility behind that speck. Emerging planets, stubborn silence, clever hypotheses, and the hard questions about how we should live. Fermi's simple lunchroom question still hums with power, inviting us to imagine, to search, and to steward our fragile conversation with the cosmos. Where is everybody? The answer may be waiting for our next telescope, our next discovery, or our next act of wisdom. Until then, the silence is not empty, it's an open space. It asks us to fill it with thoughtful search, careful choices, and a sense of wonder that stretches farther than any single star.